Before we start, one quick announcement. You're not allowed to make any recordings of this webinar for legal reasons. We will record the webinar and post a link to this on the webinar page. I'll send you the link now in the chat window here. So this is where we'll upload a link to the recording after the webinar. So you're more than welcome to look up that recording or share it, forward the link on to others, but you're not allowed to record the webinar yourself. Okay. Right, so it's my pleasure to introduce to you the speaker, Kristian Lehre. To give you a bit of a background about him, so Kristian did his PhD in Norway in 2006 with Pauline Heddo. He was a postdoc in Birmingham working with Xin Yao. And then he went to become a postdoc at Denmark's Technical University working with Carsten Witt to 2011. And since September 2011, he's now a lecturer or assistant professor at the University of Nottingham. Kristian has been working on the runtime analysis of evolutionary algorithms, and in particular, also other nature-inspired search heuristics. Amongst his achievements are statements about the population dynamics, so how to analyze a population of individuals, and that's something he's going to talk about. His work has won a number of Best Paper awards, including 4 awards at Geckos and ICSTW. He's the Vice Chair of the IEEE Task Force on Theoretical Foundations of Bio-Inspired Computation, who are working on promoting the use of theory to practice. He's given tutorials on evolutionary computations in summer schools and also tutorials at major conferences and workshops, including Gecko, CC, and Thresh. And last but not least, he's the coordinator of the €2 million EU-funded project SAGE, which is a collaboration between evolutionary computation and population genetics. Okay, so today he's going to talk about when evolutionary algorithms are provably efficient. I look forward to his talk. And we've discussed this in advance that if you have any questions, you have a button where you can raise your hands during the webinar. If you do that, I'll unmute your microphone and then you can speak to Kristian and ask a question directly. Yes, exactly like that. Okay, successful test. Yes, I'll unmute you and you can ask a question and then we'll meet you again. For most of the time, we'll keep all the microphones muted, including myself in a bit. To just hear the speaker. Okay, yeah, thank you very much for joining in, and I hand over to Kristian and hope you enjoy the webinar. Thank you.
Thank you, Dirk, for the nice introduction and also for the give this seminar. Or rather webinar. So I must say this is the first time I'm trying this, and it's a bit unusual to talk to an audience without seeing the audience. So it is great if you just interrupt me anytime. If you have any questions or anything, and then we'll just see how this goes. Okay. So as was mentioned, today I'm going to explain a little bit about how we can analyze evolutionary algorithms mathematically, or how we can prove when they are efficient and when they're not efficient. So I don't know so much about the background of the audience. So I'm going to start just describing what is an evolutionary algorithm, and I'm going to give the pseudocode of one particular algorithm so that for those who are not familiar with evolutionary algorithms, you can see what they look like. Yeah. So just start. So evolutionary algorithms try to mimic some of the principles of natural evolution. So you have a problem you want to solve, an optimization problem typically, where you have a very large number of potential or candidate solutions, and you have some way of measuring the quality of a candidate solution. So this is what we call a fitness function. And these solutions can be solution to any type of optimization problem. For example, finding the shortest route visiting all cities among a number of cities, for example. And what is typically the problem is that the number of solutions is very large. So we need a clever way of finding the best or a very good solution without looking at all solutions. And this is where the inspiration from nature comes into play. So we represent a candidate solution using a genome or a genotype. So each individual in the population somehow represents a candidate solution. Then we assign fitness to the individuals based on the quality of these solutions. And then we have some mechanism which we call a selection mechanism, which somehow picks the better individuals from the population and allow these to reproduce. And there are various ways of reproducing individuals. You can pick two individuals and have a sexual recombination, or you can just pick one individual and do just mutation. But in some sense, the genotypic information in the one or the two, or many even more in some evolutionary algorithms, genomes is somehow mixed and varied. So we get a new population with a slightly changed genetic material, and the goal is that over time, when we repeat this process many times, that we somehow get better and better solutions. Okay, so if this is a little bit abstract, let's look at a very concrete algorithm. So the first thing you need to specify now is a selection mechanism. So one type of selection mechanism is called linear ranking selection. So what we do is that we sort all individuals according to their fitness. And then, so we have a rank. So we rank all individuals according to the fitness. Then we say that the best individual has rank 1, and the worst individual has a rank 0. And now we introduce a ranking function, and this is this blue function here. And now we say that the probability of selecting an individual ranked between gamma and 1 is given by this integral. So essentially, we're looking now at the area underneath this curve here, from gamma up to 1. Sorry, I think in my figure here there should be 1 at the bottom and 0 at the top. So the best individual is the individual with rank 0, and the worst is with rank 1. So the probability now of selecting an individual with rank between 0 and gamma is this integral. Okay, and you can. So this is the integral underneath this this blue line here. So if you pick now this linear function, then we get what is called linear ranking selection. And there's a nice paper from 1991 by Goldberg and Deb that describes different types of selection mechanisms, and this is one of the examples. Okay, so this linear ranking selection, it has a parameter here in red called eta. And that eta influences the slope of this blue line. So you can imagine that if you have this just a vertical line here, then there is no difference in the probability of selecting different individuals. We have basically uniform selection of individuals. So there is what we call no selective pressure. Okay, if we pick now a larger eta, then we have a higher slope and we're having a higher bias toward the better individuals. So remember, the individuals here at the top are the ones with the higher fitness. Okay, so here is how we can use the selection mechanism in an evolutionary algorithm. So here we have an iterator t, which is counting the number of generations. So we start at generation 0. We assume now that we have some initial population, and usually we pick that initial population uniform at random. The first thing we do is then that we sort the population according to the fitness, and then we we want to produce lambda new offspring. So our population size in this algorithm and in the rest of this talk will be called lambda, this parameter. So we produce lambda new individuals, and we do that first by selection according to this linear ranking selection mechanism. So the probability now of picking an individual with rank less than gamma lambda is given by beta gamma. So that's the function on the previous slide. So we select one individual. After we have selected the individual, we need to introduce some variation. And in this particular algorithm, we're not using crossover. We're only using mutation. And in our algorithm here, a solution is just a bit string. So it's a sequence of zeros and ones. And we assume now that we have n bits. And to produce some variation, we flip each bit position in the individual with probability g over n. So g is some parameter which we will tune. And n is now the length of the bit string. So just to repeat, we sort the population and then we produce lambda new individuals, which is the next population. First by picking an individual according to linear ranking selection. So this is the selection mechanism. And then we apply mutation. We flip each bit with probability g over n. And we do this lambda times to create the next population. Okay, so this is just a simple example of an evolutionary algorithm, and there are many different types of evolutionary algorithms. And if you go to a conference like CSE or Gecko, you will find that every year there are some new algorithms that are proposed. And most often, the typical research methodology is to implement the algorithm and apply the algorithm to some test problems. Maybe several times with some repetitions to do some statistical analysis. And then one can observe how this algorithm behaves. Now, what we would like to do is something different. We would like to develop a mathematical theory that allows us to predict the behavior of these type of algorithms. So we're doing a mathematical analysis of these evolutionary algorithms, and we want to predict for any problem size how long it is going to take to find a solution. And we would also like this theory to help us to parameterize the EA. So if you have a particular function, how do we choose now the parameters of the algorithm so that the algorithm is efficient, that it quickly finds the optimum? Okay, so I'm just going to run now one simulation on a very simple problem called 1max. So we have, as I said, a bit string of length n, and the fitness in this case is just the number of 1 bits. Okay, so if you have a bit string and individual with only 0 bits, then the fitness is 0. If you have a bit string with all 1 bits, then the fitness is n. Okay, so this simple problem is used to gain an initial understanding of how these algorithms work. Okay, so we're now going to run a simulation of this particular EA on this particular problem. So Dirk, could you please paste the link to that page? So that,
yeah,
so if you have a web browser now, you can go, yeah, thank you. So let me see if I'm able to open this myself. Okay. Okay, so I'm going to explain to you now what you see on the screen here now. So let's first look at the bottom. So at the bottom we have n columns, 1 column per per fitness value. So you can have fitness 0, so that's the all 0-bit string, or you can have fitness n, which is the all one-bit string, or you can have something in between. Okay. Now you see some red lines here. So these red lines somehow describes the cumulative distribution of the population. So for a given line, we have a particular fitness value. So for example, here in the middle, it's a fitness value n/2. So you see that if this red line is, if this line is completely red, it means that the entire population has achieved a fitness of n/2. Okay, if you go here now to the bottom right, you see now that they're just a slightly, this bar is just slightly going up below 0. So this means that there's only a small part of the population that has reached this particular fitness value. Okay. Now, on the upper part here, we have a way of controlling the parameters of the algorithm. So if you move this dot now, you change 2 parameters. So along the vertical axis, you change the selective pressure of the algorithm. So this is this eta value. Okay. So if you remember, this eta value can be between 1 and 2. Moving this upwards will now increase the selective pressure. Moving it downwards will decrease the selective pressure. If you put it all the way down to 0, to 1, we get a uniform selection. So it means that we make no distinction between the individuals in the population. And you see now that the population will be distributed roughly around n/2, but there is some variance in the population. Okay. Now, if you move this thing horizontally, you change the mutation rate. Okay, so the mutation rate here is shown in this black part. So this is this chi value. So here we have now mutation rate 1.8/n. So if I increase the mutation rate, we see that there is some impact now on the population size, on the distribution of the population. Okay, so for example, in this particular setting, where we have mutation rate something like 3.8/n and selective pressure eta 1.2, then the algorithm will not be able to find optimum. It somehow gets called a mutation selection balance, so some kind of equilibrium position where the algorithm doesn't make any progress. Okay, so usually when I give these talks, I make a bet. I ask the audience to give me some parameter settings, and I will be able to predict, or I bet that I will be able to predict whether the algorithm will reach the all one-bit strings. I'm able to solve this problem. So is there somebody in the audience who would be interested in giving me 2 values, or let's say, 2 values of mutation rate and eta, and I will try to guess whether this algorithm will work or not. Okay. So Dirk, can you take someone from the audience?
Yes, yeah. Do you want to raise your hand if you want to give some parameters to Kristian? We've also had 2 questions in the meantime, so before you move on, you want to? Okay. Yep. So yes, people have forwarded these questions to you.
Can you read the question for me, maybe? Or?
Okay, so one, Tirimuna Benala placed 0.1.
0.1 for what parameter? For the mutation rate?
Let's see. Unmute the microphone. Can you hear us, Tirimuna Benala? You were the first.
Yeah, am I audible?
Yeah.
Yes, I can hear you.
Yes, sir. Yes. So actually, I've given 0.1 and 0.2 as 2 mutation values. Just I wanted to see. I'm seeing it first time, sir. I don't know about this. I'm a computer science assistant professor, JNTU, India.
Okay, excellent. So the parameter values that you want is 0.2 for the mutation rate. Is that so?
Yes, sir. Yes, sir.
And the other parameter for the selective pressure, that's eta between 1 and 2.
Sir.
So which value? Because I have to choose now a parameter for eta between 1 and 2 and a parameter for this g, which is the mutation rate. So you said 0.1 for the mutation rate.
Yes,
So
sir.
essentially it is 0.1 divided by n, okay, where n is the length of the bit string. So very low mutation rate in this case.
Okay, sir.
So which parameter setting do you want for eta?
Eta's value takes from 1 to 2, na, sir. I want 1.6.
1.6.
Yes.
Okay, so my prediction is that this will work. Okay?
Okay.
So let's see now what happens. I move now the mutation rate very, very low. So the typical mutation rate we have, at least in elitistic algorithms, is 1 over n. But now we're going to go much, much lower. We're going to 0.1. So let me see, we are 0.3, 0.2, 0. Okay, roughly here. And we want now the selective pressure to be 1.1. Okay. Sorry, you said selective pressure. What was the selective pressure? 1.6 you said?
1.6.
Yeah. So we're going up to, let me see, it's a bit hard for me to see, but it should work even for 1.5. So let's say roughly here. And now we're just waiting to what will happen with the algorithm. Okay. So you see here now that it's progressing towards the target.
Sure.
And there it found the solution. Okay, so now almost all of the population now is the all one bit string. Okay.
Okay.
So this means that, so this is an example how we can predict the behavior of these evolutionary algorithms using our theory. So you will have one exercise after this talk, or midway through this talk, where you actually are asked.
Can I ask another question, sir?
Yes, yes.
Sir, actually in genetic algorithm we are using crossover and
Yeah.
for diversity of the population. What is the exact purpose of mutation there, sir?
So the purpose of mutation, you need some mutation, otherwise the population won't be able to progress. So let's just change a little bit here now. I put mutation rate to 2.39. Okay. Now the population is moving a little bit down. Now I turn off mutation. So what I'm doing now is that I'm moving mutation to 0. Let's see what happens. Okay. You see that the algorithm progresses, but only up to some point, and then nothing happens because there is no variation in the population. So in order to have some progress, you need some variation to select from. Otherwise, you will get just copy individual in the population.
Sir, but crossover does the same thing, no, sir?
No, it doesn't. So a crossover will combine information from several solutions. However, it is a big open problem, not only in the theory of evolutionary algorithms, but in evolutionary theory in general, to understand the real purpose of crossover. And so this, we don't completely understand the role of crossover yet. But we know that there are some problems where crossover is essential. So by having crossover, we can reduce the runtime from exponential to polynomial. However, we don't have the complete picture yet, but it is related to several factors. One of the factors is the diversity in the population. If you don't have any diversity in the population, crossover is not doing anything.
Okay.
Yeah. So maybe it's an answer that doesn't completely answer what you asked for, but if you want to do research in this area, this is a very, very important problem.
Sir.
Just, yeah. Okay. So, yeah. So hopefully after this talk, you will be able to predict the behavior of this EA the same way I did now. Was there any question or?
Yes, we've got 3 people lining up for questions. Do you want to take them now?
Okay.
So we've got Rahul Gupta,
Okay.
who is asking about why crossover is not preferred. Rahul, can you hear us?
Yes, sir, can I speak?
Yes, yeah, go ahead.
Yes, I can hear you.
Yeah, so I'm researching upon genetic algorithms. So I wanted to know that do genetic algorithms and evolutionary algorithms run parallelly or they are separate fields for research? And if we research upon a same, what are the other things that can be preferred other than crossover? Because crossover is getting very backward these days. Are there any other approaches which may be better than crossover?
Yes, I mean, my opinion is that it is, as I said, it is unclear whether crossover is useful. So just a question, just first a little bit about terminology. So usually we use the term evolutionary algorithm as an umbrella term for all these type of algorithms that are inspired by evolution. And at least in the theory community, we use the term genetic algorithm when the evolutionary algorithm uses the crossover operator. So a genetic algorithm is a particular type of evolutionary algorithm which uses crossover. And there are many other mechanisms than crossovers. So for example, there are specific diversity mechanisms to make sure that you have a diverse population. One diversity mechanism could be to split up the population into parallel populations. So these are called island models. So one of the purpose of this could be to introduce some diversity because you now have separate populations that just only rarely migrate some islands. And this you can implement easily on a cluster of computers. So it's a good way of utilizing a cluster for running evolutionary algorithms.
Certainly.
Does this answer your question, or?
Sir, it does answer my question, but sir, one more thing I wanted to ask. Sir, can you please refer me something through which I can refer to genetic as well as evolutionary algorithms?
So you mean a book, or you mean a term? I'm not sure.
Slide or anything.
Slides.
Yeah,
Okay.
a book, sir.
Yeah, so there is an introductory book to evolutionary algorithms by Iben. So that's one.
I can refer for learning.
Yeah, for learning evolutionary algorithms, there is a book by Iben. So maybe we can place a reference to that book.
Okay, right, sir.
Comments after the session. Yeah. Any more questions?
Okay, I've got Mr. Islam. Can you hear us? Hello?
Yes, I'm hearing you.
Yes, yeah. Can you tell us your name and your question?
Can you hear me?
Yes, yeah, I can hear you.
Yes, I can hear you.
Okay, I'm a student of MS Master's student from University of Dhaka. I'm working on a genetic algorithm, like evolutionary algorithm. My question is it feasible to use evolutionary algorithm or genetic algorithm to solve a real-time problem where we need to solve this problem in real time, such as a task scheduling algorithm, where we need to assign these tasks in some node or computers? Hello?
Okay. Yeah. So it depends on what you mean by real time. So if you have some scheduling, some type of scheduling problem, or for example, some rostering problem, where the changes don't happen too frequently, then there is a whole subfield of evolutionary computation that deals with so-called dynamic optimization. And there are various ways of ensuring that when the problem changes, that the population will somehow be able to track the new optima. So, but it depends a little bit on the time scale. So if you need very, very quick new solutions, maybe a large population evolutionary algorithm is not maybe the ideal solution.
Okay. Okay. That means if we need a quick solution like we need some constant in time. For example, I have to get an optimal solution in 1 second, then I cannot use the evolutionary algorithm. Am I right?
It's a bit hard for me to tell. 1 second might be fine actually. It really depends on how you actually implement this algorithm. If you want very quick, if you have a very small time budget, maybe it's good to have an algorithm with few individuals. But it's very hard for me to say something very precise without knowing more about your application.
Is any other alternative solution or alternative approach to solve these types of problems in using evolutionary algorithm or some optimization algorithm?
Yeah, there are a whole range of techniques. I mean, there are many other types of nature-inspired techniques. For example, particle swarm optimization. Typically, this
Yes,
you would apply in if you have a continuous search space.
Yes.
Or if your problem is if it's not an NP hard problem, there might be also problem-specific exact algorithms.
Okay.
So in this case, it's
if we run, sorry.
Yeah. So if you have a problem which is in P, or you have an efficient algorithm for the problem, then I would recommend to use this algorithm instead of an evolutionary algorithm. This is probably quicker. Yeah.
And if we, for example, if we run the evolutionary algorithm and stop after some time, for example, 1 or 2 seconds or some specific time, then we get the current solution. That is, up to this point, what the best solution we get. I do not need the optimal solution. Then it would be a good option to use this evolutionary algorithm.
Yes, I mean it completely depends on how quickly the algorithm reaches its goal. If it takes a long time, then clearly, I mean, it's stopping the algorithm after some fixed time might be not give a good solution. But again, it depends on your application. In terms of theory, there is a subfield of evolutionary computation theory, it's so-called fixed budget computation, that provides theoretical guarantees about the quality of a solution after a fixed number of iterations. So you give the algorithm some time budget, and this theory is able to tell you what is the expected fitness or quality after that time budget. Okay.
Thank you.
Dirk, I think go on with the second part. So yeah, I had quite a lot of slides, but it's good that you ask me questions. I wanted to start on the theoretical part here, so I'll just stop this. Okay, so what we see here is to do some prediction of the behavior, and we do this using various types of techniques, and some of these techniques I'm going to present today. So first, a little bit about the philosophy behind this research. So if you think about classical algorithms, what we often want to do is to say two things about an algorithm. The first thing we want to prove is that the algorithm is correct. So you apply this algorithm to various instances, you want some guarantee that you always get the correct solution. So if you apply, for example, heap sort on some sequence of numbers, the algorithm will always produce a sorted sequence of numbers. So this is the first criteria. If the algorithm is not correct, maybe it's less interesting. The second criteria is the computational complexity. So here we are concerned about how much computational resources will the algorithm require to solve the problem. So usually we're talking about the time. And we want to compare algorithms with respect to their computational complexity. So for example, we prefer heap sort over bubble sort because the runtime of a heap sort algorithm is better than the bubble sort algorithm. Okay, so there is a very well established theory for algorithms in computer science. However, this theory hasn't really, or until some years ago, wasn't really applied to evolutionary algorithms. So what we really want to do is to apply the same, we want to ask the same questions and possibly using similar techniques to answer the question about correctness and computational complexity. So in terms of optimization, correctness means, is it possible, is it always the case that the algorithm will find the global optimum in finite time? And you can replace global optimum with maybe some approximation guarantee if that is fine with you, if you want to just have a solution that is 90% within the optimum, for example. Okay, and usually this is quite easy to prove that you have correctness. So I'm not going to talk about that aspect. The more important aspect is how much time will it take for the algorithm to find a solution. Okay, and if the algorithm, so usually when we estimate the time complexity, we estimate it with respect to the size of the instance. So we usually use the variable n to state the size of the problems. We want to understand how does the time grow as a function of n. Okay, and if that time grows exponentially with the size of the problem, so for example it's e to the power of n, then it means that this algorithm is probably not practical for this problem, because just for slightly larger instances it will take too much time. And we have polynomial time if the runtime can be expressed as a polynomial of n. So for example in heap sort you have n log n worst case running time. And this is an algorithm that can possibly be efficient. It depends on the degree of that polynomial. Now, in the case of randomized algorithms, such as evolutionary algorithms, the runtime is not the same every time you run the algorithm, because you use random bits, or you do random mutation or random crossover. So the time is a random variable. So the time will have a distribution, and then we typically interested in finding some properties about that distribution. So for example, what is the expected runtime as the function of n? Okay, so this is an outline of the talk. So I've just given the introduction now about runtime analysis, and I'm just going to present to you two or maybe only one tool that is very general and relatively easy to use, which allows you to prove statements about the expected runtime of evolutionary algorithms. And I'm going to apply this method to various examples, including the one we looked at in the beginning. Okay, so first of all, we need to specify what type of algorithms are we talking about. So the methods I'm talking about today apply to these type of algorithms that can be described in this way. So we have some search space X. So this could, for example, be the set of bit strings of length n. And then we have a population. And we say that the population size is lambda. Okay. So our algorithm stores maybe an array of lambda elements of this set X. And this is the current population. Now to get a new population, we apply some operator, which I call D. So this given this operator, it gives us a distribution over the search space. Okay, so this is an abstract way of describing a large class of evolutionary algorithms. So this operator is a mapping from a given population to a distribution over X, and we obtain the next population by sampling from this distribution. Okay, so in our first algorithm, this D operator is first selection and then variation. So we select an individuals from our current population PT, then we apply some variation, and we obtain the ith individual in the next population. And we do this lambda times to obtain the next population. So this algorithm is a non-elitistic evolutionary algorithm. And perhaps if you have applied evolutionary algorithms before, maybe you have applied elitistic evolutionary algorithms. So these are algorithms where you, in every generation, you keep the best individuals. one or two of the best individuals, something like this. Now, if you know this theory, which I'm going to present, then I'm going to show you that you can somehow simulate an elitist evolutionary algorithm with a non-elitist evolutionary algorithm. So you don't lose much by using a non-elitistic algorithm if you parameterize it correctly. And these non-elitistic algorithms can do something that elitist algorithms cannot do. Okay? So just to be a little bit more precise about the problem we're looking at, about what is runtime analysis. So we have our search space X, and we're interested in finding some subset B. This could, for example, be the set of optimal search points. Okay? So this is some subset of B here, and we define now a variable T of B, which is the minimum number of generations T, such that the population at time T contains an individual in the set B. So sometimes this is called the hitting time. Now you can see here in this expression that I have multiplied by lambda, because in every iteration, or sorry, in every generation I do lambda trials. So this TB here now corresponds to the number of individuals which have been produced until I reach my target. And the two things we're interested in looking at. So this TB is a random variable. So the first thing we're looking at is the expectation of this random variable. So on average, what is the runtime? And the second thing we're interested in is the probability that we have a success within a fixed number of steps Tn. So this is called the success probability. Okay, so the techniques which I'm going to present gives you the answer to these questions, assuming that you know something about this operator D. Okay, if you know something about how this evolutionary algorithm is implemented, then these techniques will be able, in many cases, to tell you what is the expected runtime. Okay, now there is a large literature on runtime analysis of evolutionary algorithms, and there are many different ways of analyzing population-based algorithms. So I'm just going to present two methods. This level-based method, and this was introduced last year at PPSN. And I'm not sure if we have time, probably not. There is this negative drift theorem for populations, which was presented at PPSN in 2011. Okay, there is also quite a lot of literature about runtime analysis. There are 3 books which have been published. We can also paste links to these books so you can read more about this area. Okay, so I'm just going to give you some quick introduction to this level-based theorem, which allows you to make these predictions about runtime. Okay, so the first thing we need to do is to take our and split it into, or partition it into, what we call the levels. And then we define, given a particular population in our search space, we need to define what do we mean by the current level. Okay, so we have, for any population, we have a current level if we have a partition of the search space into levels. Then I'm going to give a statement of the theorem and some conditions, and then I'm going to give some recommendations of how you can apply the theorem, and in the end, some example applications. And it's out of the scope to present the proof of this theorem in this webinar. Okay, so the first thing we need to do to apply this theorem is to take our search space and introduce some levels. And what are the correct level way of defining these levels depends on the particular problem you have. I'm going to give you some examples if you have time. Okay, so we define some subsets A1 to m plus 1 such that these subsets, they don't overlap, and if you take the union of these subsets, then you get the entire search space. And the final thing we need is that the last level should correspond to the optimum for the problem, or it is this set B I talked about earlier. And just to have convenient notation, I say that AJ plus, that's all part of the search space which is above level J. So from level J plus 1 and upwards. Okay, so here is a particular example of a search space. I have made now a partition into 6 subsets, and I have a particular population here, these circles. Now, what we need to do now is to somehow define where is the population at a particular point. So let's assume now that this is our population. So the way we do this is that we first think about some number. So this will be fixed as a constant. So let's call this gamma naught, which should be between 0 and 1. And the right value of gamma naught, it depends again on your application. So we will see some examples. But for now, let's assume that gamma naught is 1/2. Okay. Then we say that the population is at level J if we have at least gamma naught times lambda individuals above level J. So here it is AJ minus 1 plus. So this is at level J or higher. And we have less than gamma naught lambda individuals above level J. So for example, in this case, we have picked gamma naught to be 1/2. So lambda is the population size. So at what level here do we have half of the population is at level J, and less than half of the population at the level J plus 1. So if you look at this, we have now 1, 2, 3, 4, 5 individuals at level 4 or higher, but we have only 2 individuals at level 5 or higher. And in total here we have 10 individuals. So here the current level is 4. Okay, because we have 4 individuals, so gamma naught lambda, so lambda is 10, individuals at level 4 or higher, and we have less than 4 individuals at level 5 or higher. Okay, so now we're coming to this level-based theorem, and I'm first now giving you just the informal version. So what we need to show is that it is always possible to sample individuals above the current level. This is one condition, G1. The second condition is that the proportion of the population above the current level increases in expectation. And the third condition is that the population size is large enough. If these 3 conditions hold, then you can prove that the expected time to reach the last level cannot be too high. Okay, so let's now be a little bit more specific. So to use this theorem, we need some parameters. So we need the level partitioning, so we have already talked about this, and we need something called upgrade probabilities. So these are M probabilities between, so these are numbers between 0 and 1. And we say that Z min is the smallest of these probabilities. So this you need to pick. I'm going to explain how you can pick this. You need a parameter delta, which is between 0 and 1, and you need a constant gamma naught we have talked about. Okay, so now this is the theorem. So here it says, assuming that the current level of the population is J, okay, and assume in addition that at level J plus 1 or higher, we have, these inequalities should be in the other direction, so they should be greater than or equal here. Yeah, so it's in the other direction, these inequalities. No, sorry. No, it is correct. Sorry, I just confused myself. So we have at least gamma 0 lambda individuals at level J minus 1, at level J or higher, and we have less than gamma 0 lambda individuals at level J plus 1 or higher. So let's assume that we have gamma lambda individuals at level j plus 1 or higher. Then we need to satisfy this condition. So if we don't have any individuals in higher levels than level j, then there must be some probability zj of producing individuals in that higher level. And if we already have some individuals at level j plus 1 or higher, then the probability of producing a new individual in that part of the search space should be gamma times 1 plus delta. So we have a multiplicative factor times the current proportion of individuals in that level. In addition, we need a population size to be large enough. And the population size depends on all of these other parameters. If these three conditions are satisfied, then the expected time to reach the last level is this expression. Okay, so let's just explain this a little bit differently with a figure. So, sorry. So again, we have our search space, which is partitioned into these levels. We have our current population at time t, which is distributed on this level. So we assume that we have gamma naught lambda individuals at level j or higher, and we have less than gamma lambda individuals. So we have gamma lambda individuals, which is less than gamma 0 lambda at the level above. Okay, and what we need is now that the probability when we sample a new individual to end up in this level or better should be either zj if we have no individuals in this part, and it should be gamma times 1 plus delta if we already have some individuals here. So if we don't have any individuals here, we will produce some with some probability zj. If we already have some individuals at a high level, then we will expand those individuals, expand that part of the individual. Okay, so Dirk is telling me now that it's fine to overrun a little bit past 4 o'clock, so let's just go on. Okay, so this is the theorem, and this is basically what you need to predict the runtime of many of these evolutionary algorithms. So here is a kind of a recipe for how you apply this method. So suppose you have some problem. The first thing you need to do is to partition up the search space into these levels. So A1 to AM plus 1. Then you need to find two parameters, gamma naught and delta, and a configuration of the algorithm. So you need to tune the mutation rate and the selective pressure so that the condition is satisfied. So you need to make sure that if you already have some individuals at level j plus 1 or higher, then the probability of sampling individuals at j plus 1 or higher should be gamma times 1 plus delta. Okay, this is typically the hardest condition to satisfy. The third step now is if you don't have any individuals at a high level, then you just need to find a probability that you will produce some better individuals. So this is typically due to mutation or crossover, so due to the variation operators. So one question was in the beginning, if you have no variation, then typically you will not be able to satisfy this condition 3 here. Sorry, the condition G1. Okay, once you've done step 1, 2, 3, you have all of those parameters, and then you can now calculate how big the population size should be. Okay, and in the end, once you have picked the right population size, you can now read off the bound on expected runtime, which is this expression down here. Okay, so let's just do this for a very simple algorithm. I think we can finish with that example. So now I'm not talking about bit strings, just to make things easy for you. As a first example, we consider a very simple search space. It just consists of the integers from 1 to m plus 1. Okay, and we have a fitness function, which is just the identity function. So the fitness of 1 is 1, the fitness of 2 is 2, and so on. And the goal is to find the search point m plus 1, because this is the optimum in this problem. Now, we apply this very simple algorithm, but instead of using linear ranking selection, we're now going to use something called mu, lambda selection. So to produce the next population, we sample a parent X from the current population using mu, lambda selection. We obtain a new search point Y by mutating X, and we say now that the ith offspring is this Y. Okay, and we do this lambda times to obtain the next population. So what is this mu, lambda selection? So it's very easy. Suppose you have a population of size lambda. The first thing you do is that you sort the population. So the best individual is first, the worst one is the last. So you make sure that you have the fitness of the first individual is the best and the fitness of the last individual is first. Okay, and now you have this parameter mu, and this parameter mu has to be less than lambda. So what you do is that you pick now uniformly at random an individual among the mu best individuals. So for example, if mu is lambda divided by 2, to sample or select one individual, you pick randomly among the better half of the population. Okay? And to do things simple, let's consider this very simple mutation operator. So the probability now, suppose we have an individual which is at point J. Then with probability 1/3, it stays at J. With probability 1/3, it increases to J plus 1. And with probability 1/3, it goes down to J minus 1. Okay, so it's a very kind of simple mutation operator. Okay, now the first thing we need to do, step 1, is that we need to make a level partition. So we have a search space, which is just the integers, a fitness function, which is the identity function. And here, what we do is that we say that the level J corresponds simply to the search point J. Okay, so AJ plus is all integers larger than J. Okay. Now, let's go back to this definition of the current population. What does this really mean? So, the current population, let's take any population. So let's now assume that we have at least gamma, naught, lambda individuals at level J or higher. So this corresponds to this blue part. So here we have a distribution of the individuals in the search space. We have maybe the majority here at level J and some individuals at J plus 1 and so on. Okay, let's assume now that we have gamma 0 lambda individuals at level J or higher, and we have gamma lambda individuals at level J plus 1 or higher. So this is what this condition means, okay, or this assumption. Now, the mu comma lambda selection mechanism now selects uniformly at random among the best mu individuals. Okay, now it is convenient to pick this parameter gamma naught to be mu divided by lambda. So why is that convenient? Yes, it's convenient because now gamma naught lambda is just mu. So it means that if we pick this particular value of the parameter gamma naught, which is just a parameter we use in analysis, then essentially we sample uniformly at random among these individuals. Okay. So now we know a little bit about how the selection mechanism will work. So let's look now. What is the probability of selecting a parent at level J or higher? Well, since we're selecting uniform at random within these individuals, it must be 1, because all individuals are at level J or better. And what is the probability of selecting something at level J plus 1 or higher? Well, it is the proportion of the population which is at level J plus 1 or higher. So we assume now that we are in this case here that we have gamma lambda individuals at level J plus 1 or higher. So the probability now of sampling an individual in this portion of the search space is just gamma lambda over mu. Okay, so to check condition G2, we need to show that assuming that we already have some individuals up here in level J plus 1, we need to show that the probability of sampling individual in this pink region here is at least gamma times 1 plus delta. Okay, so to do that, it is sufficient to select a parent in this pink region. And then when we do mutation, that we don't jump backwards. Okay, so if we stay at the same level or we improve, then the offspring will stay in this pink region. Okay, so the probability of selecting a parent in AJ plus is, as we have seen, gamma lambda over mu. And the probability of not downgrading is 1 minus the probability that we going downwards to the left. Okay, so now we see that what we want to have is gamma lambda over mu times 1 minus 1 over 3 should be larger than gamma times 1 plus delta. And this we achieve by picking, for example, lambda over mu to be 9 over 4. Okay, why is this a good choice? Because now this equals gamma times 1 plus 1 over half. So here we can now pick delta to be 1/2, and we have satisfied condition G2. Okay, so that's condition G2. Condition G1 is when we have no individuals at the high level. Okay, so this is the case here. Then we just need to show that there is some probability of upgrading. Now, the way we can do this is that we sample an individual here and we upgrade. So the upgrade is the probability 1/3. So the probability of sampling something in this part of the search space is the probability of selecting a parent here. So this would be probability 1. And then the probability of upgrading. And that is probability, it's 1/3, as we saw with this simple mutation operator. So we satisfy now condition G1 by picking Zj to be 1/3. And this we can do for all levels. Okay. The last thing we need to do is to make sure that the population size is large enough. So we need to make sure that the lambda is larger than this expression. And so just by plugging in the values now of these parameters, gamma naught, delta, and z, here it should be set min, so the minimum probability of upgrading, we get that we satisfy condition G3 by picking lambda larger than 72 times log m plus 18. Okay? And so we have now satisfied all conditions, and the expected time to now find the optimum will be this expression. So expressed asymptotically with big O notation, it is m times lambda log lambda. And if we pick now lambda to be something like, to be exactly this expression, it is big O of m times log m times log log m. So that's relatively quick. Okay, I think we won't have time to talk a little bit more complicated algorithms. So I think I will finish here with that example, but this theorem can be applied to many algorithms. You can apply it to an algorithm like the one we looked at in the beginning of this webinar, where we have linear ranking selection and mutation. And there we need to talk about what is the selective pressure. So we get this corollary to the main theorem. Okay, you can look at the slides later. Here is the proof, an example application. You can also analyze crossover. So it's just a more complicated D operator. So here we first do selection of two individuals, x1 and x2. We apply crossover, we get an individual z, and then we apply mutation, we get an individual y. So in this case, we have this particular corollary. So it just says what should the variation operator satisfy. So mutation and crossover operator satisfy. We get some bounded runtime. We can also consider other cases where we have some uncertainty in the optimization process. Maybe when we apply the fitness function, something happens to the bit string. So we have some uncertainty before we evaluate the fitness function. Or maybe we don't see the fitness function. This is what we call partial evaluation. Or maybe there is some noise on the fitness value. We can apply some Gaussian noise term. But in all of these cases, what comes out of this theory is that if you use binary tournament selection, then it's sufficient that the probability that you choose the best is 1/2 plus some delta, some positive delta. Okay, And there is also a theorem for proving lower bounds, but I won't have time to talk about that now. So I'll just go towards the end of the talk. So just to summarize, so this rent analysis is a mathematically rigorous way of proving statements about the performance of evolutionary algorithms. So it's a different methods of obtaining results than doing experiments. And many of the previous results in runtime analysis are for relatively simple evolutionary algorithms, something like 1 + 1 EA. So we have developed some special techniques for analyzing population-based EAs. And the technique which I presented is the so-called level-based method, which was introduced last year in PPSN. And it's a very general method that can be applied to analyze very different types of algorithms. So for example, at this year's Gecko, we analyzed an estimation of distribution algorithm. And there's another theorem that tells us under what conditions the algorithm is inefficient. Okay. So before I finish this talk, let me just acknowledge some of my colleagues. So this theorem on level-based analysis was published by together with Duan Koros, who is my PhD student, Duc Wang Dang, is my postdoc, and Anton Ermev, he's a collaborator from Omsk branch of Sobolev Institute of Mathematics in Russia. And this research is supported by an EU project called SAGE, which is Speed of Adaptation in Population Genetics and Evolutionary Computation. Okay, thank you. So I hand over to Dirk now.
Okay, yeah, thank you very much, Kristian, for this very interesting talk. We are slightly over time, so I mean, I don't blame anyone if you want to drop out now, but we've got some time for anyone who wants to stay on to discuss some questions. We've got 3 people lined up who have had their hands up. Yeah, maybe we can just go through them one by one, and more people are coming in. Let's start with Ebenezer Popula. You've had your hand up quite a while. Do you have a question for us? Can you hear us? Do you have a question?
Yeah.
Yeah.
Yeah, I have a. Yes, I can hear you. Can you hear me?
Yeah. Yes, we can hear you. Yeah.
Okay. Yeah. Now the question I have is, in a situation whereby you have up to 2⁻41 possibility of solution, and you're looking for a best solution, in such a so in such a way, how do you kind of separate up your population so that you can actually search the space in an optimal way? Is there a way?
So I think I didn't get the first part of the question. So the assumption was that you have a large search space?
Yeah, I have a large subspace. Actually, yeah. So this subspace is about 2⁻41. I'm trying to look for a possible set of combinations.
Okay.
Yeah.
So
yes.
I'm not sure if I'm familiar with your problem domain. Yeah. So the question is how you can efficiently find the optimal solution.
Optimal solution. Yeah. We are having a very large subspace. Yeah.
Yeah. So let me first state that it's not necessarily the case that a larger search space is more difficult than a smaller search space. So it depends also on the structure of the search space. So let me just go towards the beginning of the talk. So this was actually also this simulation. So if you look at this problem called 1max, I'll just give you the definition. So the 1max, we just count the number of 1 bits. So here we have a very large search space. If you have n bits, it's 2 to the power of n possible solutions. However, this problem is entirely trivial. It's very easy for the algorithm to find the solution just because there is no interaction between the variables here. So although this problem is big, we can solve it efficiently. So only the size of the problem is not always sufficient to determine whether the problem is hard. It depends on many other aspects as well. So my best, what should I say, my best advice, or one suggestion now after this talk, is if you want to determine whether it is possible to optimize this problem efficiently, is to try to satisfy the conditions of this level-based theorem. So is it possible that you can find some partition of the search space? So you define kind of different levels of solutions in your search space such that the algorithm satisfies these conditions, so that it's able to always produce better individuals, and once you have found better individuals, you kind of accumulate more and more individuals in the population, and you have large enough population size. If you have those conditions, you have there should be a good chance that you will be able to find a good solution, find an optimal solution quickly. There's another method called drift analysis. It's a bit different, and it's easy to apply if you have single individual algorithms. So you measure now the distance to the optimum, and if the distance to the optimum on average reduces in expectation, then you can estimate how long it will take to reach the optimum. But it's very hard to judge without knowing quite a lot of details about the problem whether it is possible. If what you know is that if the problem is an instance of an NP-hard problem, then it is likely, it's very unlikely that you will be able to solve all instances in polynomial time or efficiently with an evolutionary algorithm. So I think you should first check if this is a case of a classical problem from the list of NP-hard problems. If there already exists some efficient algorithms for this problem, you shouldn't use an evolutionary algorithm.
Okay.
Yeah.
Okay.
Yeah. Thank you.
Yeah, thank you.
Okay, yes, before we go to the next one, let me just, before I forget, say that I've pasted links and information about the 3 books that were mentioned that were on the slides in the chat window. So if you open your chat window in your client, you should find information there, and you can just copy and paste. Then you have that available. The next person who asked a question is Andrea Mambrini. Can you hear us, Andrea?
Yeah.
Okay, yeah, fire away.
Yeah, so can you hear me? Yeah. So my question is, so of course this theorem is able to find the upper bound for the runtime when there is population and non-additive, but can be used to find, for example, for some problem, is it possible to find a situation in which a population is better than having just one individual, or in which having non-elitism is better than having elitism?
Yes, so that hasn't been published so much about that, but so these non-elitistic algorithms are less easily trapped in seemingly good solutions. So for example, if you have some uncertainty in the problem, so for example, you have a fitness plus some Gaussian noise, then having an elitist algorithm can sometimes be detrimental, because just due to random noise, the algorithm might think that it has a very good solution and keep that solution. Or if you have a 1 + 1 EA, the algorithm can get stuck as well. So we have some papers we have a paper from Foga 2015 where we analyze population-based evolutionary algorithms, so non-elitistic algorithms under noise, where we show that having this population is very useful. Then there are also some ongoing work showing that if you have a very rugged landscape and you tune the mutation selective pressure correctly, then you're better able to overcome local optima or the rugged landscape using a non-elitistic algorithm. But that's just
it's not using this theorem, right?
Yes, it's using this theorem.
Okay. So with this theorem, it will show that the runtime is the same than the elitist one, and then with some other way, this
so there's a variant of this theorem which can be used to analyze these rugged landscapes.
Okay.
But this is unpublished work. So see some upcoming conference or journal.
Okay.
Yeah.
Right. Next person is Mamoudou Zanyang. Can you hear us? Mamoudou, can you hear us?
Sorry,
Hello?
I can't hear you.
Yeah. So I can't really hear what you're saying. Whether there is someone
Maybe
speaking in the first
place. The question.
Yeah. Okay, yeah. Yeah, sound quality. Yeah, okay, so yeah, you could just type your question in the chat. Ah, okay, right. It was answered. He's typing. Okay, right. Thanks. Let's move on. And finally, we have Trimuna Benala again. Hello, you've got another question? Yeah.
Am I audible, sir?
Yes.
Sir, I have a question here. If the training data size is small, how do the evolutionary computation place itself to optimize in those kind of problems? Like, for example, say in the domain of software cost estimation and all, where the training data set sizes are very small. Then how do I apply there?
So when you're talking about training sets, maybe are you talking about some kind of classification problem, or so you have a test set and a training set, or?
Prediction problem, sir. It's a regression problem. Prediction.
Oh, okay, yeah. So, and your question, what was your question again?
Sir, suppose I'm applying neurogenetic framework to solve a prediction problem, then the problem here is that the training data set size is very small. So obviously my cross-validation is not up to the mark as per the standards, because when I go for cross-validation I have to divide, that's a k-fold I go for. So then the number of training data will be very less.
Yeah. So I think it's a very interesting application, and it would be very interesting to try to apply these methods, these theoretical methods, to answer questions about that problem domain. However, currently we haven't looked at that, so I'm not able to give you any answer based on these results. I think machine learning is a very interesting area, but I think that's a topic for future work, I think.
Sir, I want to wrap up with another query. Sir, in differential evolution, we are using the front-end mutation, then we are going for crossover. But in GA, we are going for crossover first, then the mutation. How do they vary in their functionality in usage while optimizing?
Yes, I think you can do maybe you can do both in genetic algorithms. I'm not sure what is the most common. I mean, what I showed in these slides, I didn't talk much about it. I did mutation after crossover. I think I'm afraid of giving any too precise answer to that question because I think it depends on many factors. For example, what is your search space? Are you talking about permutations or bit strings or yeah? So
Re-encoded.
real encoded, yeah.
Yes, sir.
Yes. Yeah, I'm sorry, I'm not able to answer that question actually.
Okay, sir. Fine, sir. Thank you, sir. Thank you very much.
Yeah. Yeah.
Okay. Yes.
Okay.
Yeah. Any other questions? Okay. Yeah. No one raises their hands. So yeah, I think then we're done for today. So yeah, let's thank Kristian again for this very nice talk. We've had audiences from 6 different continents, which is a fantastic result. So depending on where you are in the world, say have a good afternoon, have a good evening, or a good morning.
Thank you.
Okay.
It was great fun, and thank you again for inviting me.
Okay. Thanks everyone attending.
Yeah, and the slides and yeah, slides and everything will be available. I think that we will put a link somewhere so that you can see the parts that we didn't talk about. And you're very welcome to send me an email if you have any questions.
Okay. Yes. Okay. Thank you very much. Thanks everyone.
Thank you.
Okay. Thank you. Bye.